You.
Well, how about you?
Good. Let me guess. Partial fractions.
Yep.
Good. Okay. Do you have some problems you want to do, or you want me to?
Well, first, let's.
Is it possible that we have the same book? You don't use this book, Larson, Hostetler, and Edwards, do you?
No. Mine is by Stewart.
Okay.
James Stewart.
Okay. Well, that's good. That means probably the examples I have in my book you haven't done yet.
Yeah.
Okay.
It's just, I'm confused about the different types of cases.
Yeah, I'm not surprised. It's pretty confusing. I think I understand it at this point. We've got situations that I think you're referring to is where we have distinct linear factors. Another case might be repeated linear factors. Another case might be distinct linear and quadratic factors. And a final case would be repeated quadratic factors. Do you want to go through each one of those? I've got a problem on each one, if you like.
Sure.
All right, we'll start with distinct linear factors. Okay, if you factor that, what do you get?
X plus 3, no, minus 3 times X minus 2.
Okay. So that's the first step. And then we want to figure out how to represent that as the sum or subtraction of two quantities. In other words, we can't integrate this. But if I can get it into an a over x minus 3 plus a b over x minus 2, if I can figure out what a and b are, then I'll be able to integrate that separately.
Okay.
So that's the concept of partial fractions. I'm going to turn my camera off again. I'm going to have to contact GoToMeeting and ask them, how do I solve that problem?
Yeah.
Okay, so how do we solve for A and B? Well, we know that if we started with this and we were trying to combine it into one, in other words, if we're going what we usually do, which is the other direction, then then I can say that A times x minus 2 plus B times x minus 3 would have to equal 1, because I have this 1 up here.
Okay.
Okay? In other words, if, just in case there's confusion, if we started with that and I said add those two together, you would multiply the left side by x minus 2 over x minus 2 and the right side by x minus 3 over x minus 3, and then we would have this in our numerator.
Yeah.
And since we already know that the numerator is 1, we can say that has to equal 1.
Okay.
Okay? At this point, we don't necessarily want to distribute. It's easy to solve for A and B here by picking convenient values for x. In other words, this equation has to be true for all x. So if I say let x be 2, then immediately this becomes a times 0
Yep.
plus b times minus 1 has to equal 1, therefore b has to equal minus 1. And likewise, if I say, well, let's let x equal 3 so I can eliminate the b term, and then I've got a equals 1. Do you see that?
Yeah.
Okay. So I've solved for a and b, relatively simple here. It becomes 1 minus 1. And then that becomes easy to integrate. I've got the integral of 1 over x minus 3 dx minus the integral of 1 over x minus 2 dx. What is this integral?
X squared. Wait. Let's see.
Actually, this becomes natural log of x minus 3, and this becomes natural log of x minus 2
Yeah.
plus c. In other words, whenever you see just something in the denominator, think natural log. Now, if it was x squared, I couldn't do that. But notice that when the derivative of this is just 1, so I don't have a problem with the variable anymore. In other words, if I go to take the derivative of this to see if I get 1 over x minus 3, I do. Precisely. It's 1 over x minus 3 times the derivative of the inside, which is just 1. In other words, if this was x squared, then the integral would not be natural log of x squared minus 3. Okay. Let's take a second situation. Linears, distinct linear factors are pretty easy. Let's try repeated linear factors. Okay, first of all, I'm going to factor an x out. So the denominator becomes x times x squared plus 2x plus 1, which becomes x, I'm running out of room, hold on. Let me go down here, which becomes x times x plus 1 squared with the numerator here. Okay, so now we have a quadratic, no, I'm sorry, we have two linear factors here. It's just one of them is squared. This is repeated linear factors instead of distinct linear factors. Well, when I find this situation here where I have a linear factor that's squared, I have to allow one term for, in other words, I need an a over x plus a b over x plus 1 plus a c over x plus 1 squared. Okay? In other words, this x plus 1 squared forced me to have an x plus 1 and an x plus 1 squared. And notice that if we had started with these three fractions and I said find a common denominator, it would be this. Okay? So now I can do the same process. I can say that a times x plus 1 squared plus b times x plus 1. Hold on, let's see.
Would the A1 be times x plus 1 cubed?
No, because notice that if we had to find a common denominator here, it would not be the product of these three denominators. It would merely be x times x plus 1 squared. So that's our common denominator, and that's what we have to multiply both terms by. And when I multiply a by x plus 1 squared over x plus 1 squared, I get it in the denominator and I get this in the numerator. And b needs to be multiplied by x times an x plus 1 over all over x times x plus 1, and that will give it the proper denominator. And then c needs to be multiplied by just x. And all of that has to equal this numerator on the other side, 5x squared plus 20x plus 6. Let's make sure I did that correctly. Yes. Okay. Again, if we want to solve for a, we can let x equal 0. Notice that if we let x equal 0, this term disappears and that term disappears, and I will have a times 1 is equal to 6. So if I let x equal 0, I end up with a equals 6. You see how I got that?
Yeah.
Okay. Now, if I want to solve for c, I can let x equal minus 1, and the a term and the b term will disappear. So if I let x equal minus 1, then c times a minus 1, both of these terms will disappear, and I will have over here, that's going to be equal to 5 minus 20 plus 6. So that would be minus 9. No, hold it. 5 minus 20 plus 6. Yeah, that's minus 9. Therefore, c is equal to 9. Okay. Now we need to solve for b. And the most convenient choices for x we've used already. So you can pick any other value for x, and given that we now have an a and a b, in order to solve for b, we'll pick any other value for x. Well, we've used 0 and we've used minus 1. Let's try a 1. Okay, so a is 6, so we've got 6 times, 1 plus 1 squared, plus b, which is we're trying to solve for, b times 1 times 2, plus c, which is 9 times 1, has to equal 5 plus 20 plus 6, 31. Now that allows us to solve for b. And I'll just do it quickly. It equals minus 1.
Okay.
So that's easy enough to do.
Yeah.
In other words, that's not a complicated situation. The only thing tricky about this is knowing that you need a term for the 1 over x plus 1 and you need a term for the 1 over x plus 1 squared. If this was a 3, like that,
Right.
then we would need a plus d over x plus 1 cubed. We would need all three or all four of those terms. Okay?
And the common denominator would be x plus 1 cubed.
Well, it would be x times x plus 1 cubed.
Right. Okay.
And that's kind of one way to look at this, is how would you do it if you were going backwards? If we started with this, and we were trying to add those three, I would not use x times x plus 1 times x plus 1 squared as my common denominator. I wouldn't need to. Because all I need is a least common denominator, which is going to be x times x plus 1 squared. Notice that all of these denominators divide evenly into that common denominator. And so when we start with something that already has that denominator, we have to separate it into all three of these, not just two of them. Because it's entirely possible that we have this term in our separated partial fractions. All right, let's go to a quadratic case, because this is where it starts to get a little more complicated. Distinct linear and quadratic factors.
So getting the values for A, B, and C is the same as evaluating?
Well, not on these, it's not. When you have strictly repeated linear factors or distinct linear factors, you can solve for A, B, and C using the technique we just did.
Yep.
The previous two problems. When you get it a little more complicated, you can't do that. This will demonstrate it, I believe. Notice that we can factor that, but we can't factor this. This is an irreducible quadratic, x squared plus 4. Okay, so I need to break it into three terms. I need a over the x. I need a b over the x minus 1. But then for this, because it's a quadratic, I need a cx plus d over the x squared plus 4. Like that. And I still have my same numerator. So now when I want to write my equation starting on the right side, I would need to multiply a times x minus 1 times x squared plus 4, and then add it to b. What do I need to multiply the b by?
X times x squared plus 4?
Yes. And then the cx plus d, what do I need to multiply that by?
X times x minus 1.
Okay. Let me distribute this quickly. Oh, hold on, I'm on the wrong problem. Let's see. Okay. When I'm all done, I get the numerator that was on the left. Let me write that. That's no longer visible now, but that has to equal the above, this. So let me not rewrite that out. Okay. So now, let's see, are there any convenient values that we can set x to that will allow us to solve for one of these variables?
0.
Okay, that'll get rid of the b and the c term, and we'll have minus 8 will have to equal, if we let x equal 0, minus 8 is what we get there, and when we plug in x of 0 here, we get minus 4a. So a has to equal 2. And what else can we let x equal to and solve for another letter?
1.
Okay, so if we let x equal 1, then the a term and the c and d terms will disappear, and I'll be able to solve for b. So let me just do that. B is equal to minus 2. Okay, now it gets a little tricky because there's no longer anything we can let x equal to conveniently that will get rid of a and b, because notice that we can't get rid of it. We can't make this term 0.
Yeah.
So to find the two remaining constants, we need to pick any values for a, and that's going to give us two equations and two unknowns. So let's pick another simple number for x, which is minus 1. And now we know that if we let x be minus 1, this becomes minus 2 plus 4 minus 8. So the left side would become minus 6. And that's going to equal 2 times minus 2 times 5 plus a minus 2 times minus 1 times 5 plus a minus c plus d times a minus 1 times a 2, minus 2.
Yep.
Okay, and that simplifies to 2 equals minus c plus d. So one equation, two unknowns we can't solve, but we can pick another value for x and generate a second equation.
Okay.
The next easiest x to pick is x equal 2. And if you go through the same arithmetic that I just went through there, we're going to get 8 equals 2c plus d. And that's our second equation, and we can combine it with this other equation and solve those two systems, and we get c equals 2 and d equals 4. And for this one, let's make sure we go through and get the final solution. So we end up with going to be the integral of a, which was 2, over x minus, because b was minus 2, so that second term is a minus, over x minus 1, plus c was 2, and it's 2x. Notice we now separate that. Originally we had that as cx plus d over x squared plus 4. Well, now we're going to separate it into the c term and the d term. C was 2, so it's got to be 2x over x squared plus 4 plus the d, which is 4 over x squared plus 4. And that's a little bit of a tricky part there. Because I could have written that 2x plus 4 all over x squared plus 4. But that's kind of hard to integrate. Notice that 2x plus 4 all over x squared plus 4 doesn't integrate nicely. But if I separate it into two fractions, you know, by just splitting it into that and this, which I'm allowed to do, then we have fractions that are easily integrated. This one is very easily integrated. Let's do it.
ln2.
Actually 2 natural log of x. In other words, we're going to remove that 2 outside the, and then we'll have 1 over x, which will be natural log of x times 2. And then the second term is going to be minus 2 times, natural log of x minus 1. Plus, notice that this does become natural log of x squared plus 4 because we have that 2x in the numerator, and that 2x is the derivative of the inside. So we're always looking for that. We're always looking for a function times the derivative of the inside. We're looking for a composite function times the derivative of the inside. We see it there, so we can essentially just apply the power rule. If you're not comfortable with that, we can go through how to use substitution to figure this out. And then this last term here is the arctan. I don't know if you went through doing these. You and I haven't done these.
No.
But
4 arctan x squared plus 4.
Yes. In other words, there's a formula for doing arctan that's a little bit more dynamic than when you first learned how to differentiate arctan. And
Actually, I have the formula for that.
okay, good. Well, it becomes then 2 inverse tan of x over 2 is what that, the integral of that equals. And then, of course, plus c. Okay?
Yep.
All right, and let's try the last most complicated case that my book covers, which is repeated quadratics. If we have something like this. And notice that we do not want to factor that numerator. If we factored it, we'd just have to redistribute it if we're going to try to solve this using partial fractions. So this denominator becomes what?
Let's see. So you want to factor it further?
Well, yeah, let's first of all figure out what we're going to have in the denominator. I know I'm going to need 2 terms, right? Because I need 1 term for every power that this quadratic is being raised to. So I need one denominator that looks like this, and I need another denominator that looks like this. Well, because these are quadratics, my numerator has to look like this in both cases. Okay? Now we've got 8x cubed plus 13x is going to be equal to ax plus b times x squared plus 2. plus cx plus d. Right?
Mm-hmm.
Okay. Now this is, we're going to use a different technique to figure out the coefficients here. We're going to go ahead and distribute this. And after distribution, I get ax cubed plus 2ax plus bx squared plus 2b plus this cx plus d. And now what I'm going to do is equate coefficients. First of all, I want to gather together all my like coefficients over here. I only have one x cubed, so I'm going to do that. But notice I have a 2ax plus a cx. Well, and I only have one x squared. Hold on. Let me go ahead and list the next x squared term, because I only have one of those. But then I have I can factor out 2a plus c as my coefficient for the x term, and then I just have a d term. Okay? In fact, no, I have this 2b here that I didn't do anything with. Well, notice there's no x with the 2b and there's no x with the d. So my constant has to be 2b plus d. This polynomial has to equal that. And now I do something that's called equate coefficients. The only x cubed term on the left is 8x cubed. That means a has to be 8. The x squared term doesn't exist on the left, which means b has to be 0. The x term coefficient has to be 13, so I can say that 2a plus c has to equal 13. Mm-hmm. And I can say that 2b plus d has to equal 0, because there's no constant on the left either. Okay, this allows me to solve for c. If I've got 16 plus c equals 13, c must equal minus 3. And if b is 0, d has to be 0. So I've solved for a, b, c, and d. And now I can rewrite it as the integral of 8x cubed plus 13x all over x squared plus 2 squared is equal to the integral of ax plus b over x squared plus 2, which means 8x over x squared plus 2, plus the only other value we had was c, which was minus 3, and it was cx plus d, so it has to be minus 3x, d is 0, over x squared plus 2 quantity squared. Mm-hmm. So now I want to take those two integrals instead of the one, and the first one integrates nicely. What's this going to integrate to? The reason I said it integrates nicely is it doesn't integrate perfectly, because the derivative of the bottom is 2x, and we're looking at 8x on the top. So different courses teach this differently. I'm not sure how you've been taught. Is this an integral that you know how to do, or do you first factor out a 4
Well, yeah, I would probably factor out a 4.
Okay, so we'll make it look like this just to make it a little easier to do. Now we can essentially apply the power rule perfectly to it. In other words, that's got to be natural log of x squared plus 2. Because the derivative of the bottom is exactly in the top. Take the derivative of this and you get this. Okay? Now, the second one, let's see. The second one actually factors rather nicely, or we can just use the power rule on it also. In other words, if we were to solve this using U substitution, maybe we should go through a U substitution problem.
Okay.
Unless you're comfortable integrating that term. This second term here,
Yeah.
if we go through a U substitution, what will we let U equal?
X squared plus 2.
So du dx would equal,
2x. Yeah.
well, we see that 2x dx right there. So we can substitute for 2x dx du. So this becomes the integral of du over u squared. See how that works? I did it a little differently than the last time I went through substitution with you. Last time I went through substitution with you, I solved for dx and then substituted that. Well, this time we're going to eliminate that extra step that isn't necessary. In other words, once we get it to here, that's what I'm looking at in the numerator over here is 2x dx. So I'll just go ahead and directly substitute du for that.
But that's the previous term, isn't it?
No, that's the second term that we're doing. Oh, excuse me. Yeah. Yes, exactly. Okay, so what do I need to do to make that 2x? I need to factor out a what? I need to factor out a minus 2/3.
Right.
So in other words, this becomes that. Oh, no, I need to factor out a minus 3/2. That's what I need to factor out. In other words, we want to turn this minus 3x into a 2x, a plus 2x. And I can do that by factoring out minus 3/2 from inside the integral into this. Notice that if I put it back in, it changes that back to the minus 3x.
Yeah.
Okay, so now I'll recognize that. And it will become this. Like that. Is that better? Sorry, I didn't mean to confuse myself and you at the same time by referring to this term over here. You're right, that was the previous term. Okay, and now that integrates nicely. It's what?
Let's see. Where am I? Just ln.
Well, no, we basically got u to the minus 2 du. In other words, let me rewrite this. U to the minus 2 du. So just use the straight power rule.
Okay.
Add 1 and divide by the new exponent.
1 over.
So it'd be u to the minus 1 divided by minus 1 still times this minus 3/2. Okay? So resubstituting back in x squared plus 2 for u gives me a minus 3/2 times x squared plus 2 to the minus 1. So let's make it 1 over x squared plus 2. And this minus 3/2 becomes a plus. The minus and minus cancels to a plus. So that is the integral of the second term. So our answer becomes plus 3/2 over x squared plus 2. Plus c. And I think we've covered all of the 4 types of partial fractions that you're liable to deal with, that you have to face. It's hard to imagine what else would be more complicated. We've covered 4 specifically different types that require 3 different kinds of solutions to solve for A and B. One, we can pick convenient values for x. The other, we have to solve 2 equations and 2 unknowns. And the other technique is we're going to equate coefficients. Which was what we used in this technique, this problem. Okay, do you have any that you'd like to try?
Actually, not really.
Okay.
I have some written down, but they're pretty similar to what we did. So.
Okay. I've got some in my book if you want to. We got another 13 minutes here. Want me to just pull some out of my book that are from the back of the exercises? In other words, these aren't examples. I've gone through the 4 examples.
The other option is I have to learn arc length too.
Okay.
It's just a completely different unit, but maybe we can save that.
Yeah, interestingly enough, arc length is harder than volumes of solids of revolution. And I'm not positive about this, but I think it's because it's multivariable. In other words, everything up to arc length is single variable calculus. We're always doing dx or dy. Well, when you are analyzing arc length, you're breaking up each arc into a hypotenuse. And that hypotenuse is equal to the square root of delta x squared plus delta y squared. In other words, if we try to find arc length by the same techniques that we do everything else in calculus, which is use Riemann sums, in other words, my arc becomes a bunch of straight lines that are infinitely small. Okay? But each straight line is basically the hypotenuse of a triangle, and the hypotenuse of that triangle is going to be the square root of the change in x squared plus the change in y squared. So all of a sudden we have a delta x and a delta y, where essentially you can think about integrating to find arc length as integrating along the x and the y axis. So arc length and surface area, which is tied to arc length, the next thing you'll do is surface area, because you need arc length to find surface area. But it definitely is tricky. It's actually kind of fun to go through the math of how they came up with the formula for arc length, because it is some real out-of-the-box thinking. I mean, it's almost like you say to yourself, well, nobody would do that in a million years unless you knew you were supposed to do that. But it's pretty clever, and if you like clever math, it's worth following their logic as to how they come up with the formula for arc length. If I remember right, the formula for arc length is 1 minus, no, it's the square root of 1 minus dy dx squared, right?
Mm-hmm.
I think that's it. Or it can be 1 minus dx over dy squared, dy. Either one works for arc length. That's what makes arc length tough. But the only part that's tough of arc length is the original figuring out what the formula should be for it. Once you are told the formula for arc length, then it's relatively simple, and it's pretty much plug in and solve. No matter what the function you're giving, you just have to take the derivative of it and square it and plug it into what we were just looking at. So arc length really is not that tough once you get behind the logic of how they came up with it. So let's see. In the last few minutes here, let me see if I can find some partial fractions that look interesting.
Okay.
Yeah, here's one that looks like it could be fun.
I hope we're not going to be learning surface area because we only have one day of class.
Oh, really? Okay. Well, you probably aren't then. You probably end this calculus course with arc length. Yeah. Well, I don't know. One day might be enough. Surface area is kind of the last thing that there is to learn in that regards. Yeah, area, volume, arc length, and surface area pretty much covers everything in the way of solving for geometry and calculus. So you might. Don't be surprised if you do learn surface area, although it's the toughest of all of them, I think. All right, so if we try to do this by partial fractions, clearly we need to factor the denominator. What does that look like?
Can you do x plus 2 times x minus 2?
Well, it's difference of cubes.
Right.
And difference of cubes factors into, if I have a cubed minus b cubed, I can factor that into a minus b times the irreducible quadratic, a squared plus ab plus b squared. Okay. So that's how I want to factor the difference of perfect cubes. And you can also factor the sum of perfect cubes. That factors also. Notice the sum of squares does not, but the sum of odd numbers does. In other words, a to the fifth plus b to the fifth also factors, but a to the fourth plus b to the fourth does not. Okay, so if we're going to use difference of cubes here, what does this factor into? X minus 2. What's the rest of it?
Plus 2
x. The easiest way to do these is to actually say a is going to be x and b is going to be 2, and then do it. Because sometimes it'll be a lot more complicated. In other words, this could be 27x cubed minus 8, and it would still be the difference in perfect cubes. It's just that a would then be 3x instead of x. Okay, so it factors into that. So it looks like we need two terms. What are they going to be?
Let's see. So 6x over x minus 2.
Well, what we're basically,
Or, sorry, a over.
yeah, what we're really doing is saying, yeah, here, let me, without having to rewrite everything, let me just do it like this. So we're saying 6x over this is going to equal sum a over x minus 2 plus, and this second term has to have a bx plus c because it's a quadratic. If it was a cubic, then you would need a bx squared plus cx plus d. I'm pretty sure. Not 1,000% sure on that, but I'm 95% sure. Okay, but with a quadratic, we need at least that. Okay, so now we can say what?
So 6x equals ax squared plus 2ax plus 4a plus x minus 2.
Okay, I guess we need to FOIL that, don't we? Okay. Now we're going to gather like terms. Well, yeah. Yeah, let's gather like terms and simplify first. Because it's, first of all, it's hard to tell whether we're going to be able to find convenient values of x and make some of these a, b, and c's disappear to solve for this thing. In my head, I can't quite see it. But I know that after we put it together and simplify, we'll be able to see it. So what's the first term I want to write over here after I gather all this together and factor out coefficients?
Just a?
Well, we've got an ax squared and a bx squared. So if I wrote ax squared plus bx squared, factored out the x squared, I would have a plus b times x squared. That takes care of that term and that term. Okay, now let's look at our x terms. We've got a 2ax, a minus 2bx, and a plus cx. So let's factor out x from that and list our coefficient as 2a minus 2b plus c. And that takes care of that term, and that term. And everything else has to be part of the constant. So plus 4a minus 2c. And if it helps to think about it, I can put parentheses around that. So now, let's see what we can do here. If we let x equal 0, then 4a minus 2c would equal 0, right? But we already know that. In fact, instead of doing it that way, let's do this the equating coefficients way. There's no x squared term on the left. Therefore, a plus b has to equal 0.
Okay.
And 2a minus 2b plus c has to equal 6. And finally, 4a minus 2c has to equal 0. And you want me to go through how to solve 3 equations and 3 unknowns, or are you comfortable with that?
Yeah, let's go ahead and do that.
Let's do it?
Yeah.
Okay. What we do is try to eliminate, the way I do this, now there may be a simpler way here since 2 of these equations don't have all 3 variables in them. Let me think about that for a second. No. The quickest way I can think to do this, the way I usually do this is I eliminate one variable between equations 1 and 2, coming up with equation 4, and then I do the same thing with equations 2 and 3, eliminating the same variable, coming up with equation 5, and equations 4 and 5 are only in 2 variables. And now you can solve it. So if I multiply the top equation by 2 and add it to the second equation, I get for equation 4, 4a, the b's cancel, plus c equals 6. Right? Now I want to come up with an equation 5 that I get from putting together 2 and 3. No, I don't need to. In fact, I can use equation 3 directly as my equation 5 because I've eliminated the b from equation 3 already. So my equation 3, or my equation 5, so to speak, is this. Now, if I subtract equation 5 from equation 4, I eliminate the a's, and I get c minus a minus 2c, which is 3c equals 6, c equals 2. If c equals 2, then a equals 1, substituting in for there. And if a equals 1, b must be minus 1. So now we've got that integral is equal to a over, what were my terms? X minus 2 minus b over x squared plus 2 plus c over x squared plus 2. Was this squared? Oh, no, excuse me. Wasn't x squared plus 2, it was the other factor. It was x squared plus 2x plus 4. And that was a bx plus c, was it not? Here, let me go back. These partial fractions, one sheet of paper is never enough. So it was bx plus c over that. Again, I'm going to split it up. Notice my bx plus c, b was minus 1, so it's minus x plus c, which was 2. So there's my second integral. No, I don't need to split that up. Oh, yes I do. Hold on a second. Let's see, the derivative of the bottom is 2x plus 2. Okay, you're good with how we got to here?
Yeah.
Okay. Well, the integral of the left is what?
ln of x.
Okay. Now the integral of the right. You know what this is? This is I think this might be a complete the square. Huh.
Yeah, it looks like.
I think maybe we do have to break this up into x over that and then 2 over that. If I factor a negative 1 from the top, I get negative x minus 2. Well, right offhand, I can't see how to integrate that. So let's break it into 2 integrals. Maybe that'll help. I'm going to have minus x over that, which will make it a plus. And then I'm going to have minus 2 over that. Now this one I can integrate by completing the square in the denominator and using the arc tan. The inverse tan on that after I've completed the square. That's something we haven't gone over either. And it doesn't look like we're going to have time to do that now, but it's essentially putting this denominator into an x minus or plus something squared plus a number. And then it looks a lot like 1 over x squared plus 1. And the integral of that is arctan. So you end up using that arctan formula. As far as this one goes, I'm not sure how to integrate that. It's been a while since I've had to integrate these complicated polynomials. That's why trig substitution is so valuable, is that most polynomial functions that you go to integrate end up being hard to integrate as polynomials, just really hard. So by using trig substitution, you can turn everything into trig functions, which are easy to integrate. And in case you're wondering why we only learned sine times cosine and tangent times secant, is because I think pretty much any combination of trig functions can be narrowed down to one of those two.
Yeah.
Maybe if you had cotangent times cosecant, we'd use the same method that we use on tangent secant. So I'm pretty sure that any combination of trig functions will allow you to use those two methods that we learned with sine to the m cosine to the n and tangent to the m secant to the n. But right off the top of my head, I can't think of how to do that.
That's okay. I mean,
yeah, it's not like there wasn't any hard material in this session.
yeah.
Okay, well that's a pretty good primer on partial fractions at least.
Good.
Okay.
Yeah.
All right, Dominic. So you have one more day of class and then you have a final?
Yeah, it's actually not until Thursday.
The final? Okay.
Yeah. So I'll probably be beginning with you.
Okay. Yeah, if you need another session to go over arc length and surface area or more of this even, that's fine. And if my schedule looks filled up, it's just that in the summertime I kind of block out the days so that I can play golf if I want to. If you can schedule it before 10 or after 6, that's fine. If you can't, if you need something in between, by all means call me, and I may not be playing golf that day. So if you're looking for a session on Thursday,
Probably Wednesday.
Today's Wednesday.
Next Wednesday.
Oh, next Wednesday. Okay. Yeah, that's fine. Like I said, if you can't do it before 10 or after 6, call me and I'll go ahead and schedule it, and I'll work my golf around it if I decide to play golf.
Okay.
Okay? So I don't leave it wide open, because somebody might just pick 1 o'clock or something, and then that just kills my day.
Yeah.
And if 1 o'clock's the only time you can do, then that's fine. I'll do that. But most people can do it at a lot of other times also. So.
Yeah, that'll be fine. I don't have anything else going on or things.
Okay. Well, enjoy your class tomorrow. It will be surface area, I'll bet you anything.
Great.
Okay? All right, Dominic.
All right.
Talk to you
Thank
next
you.
week. Bye-bye.